So up to now with the examples I've done, we've been under the assumption or we've been told that the integral is going to converge. But most of the time you're not told that in advance. And so you need to first predetermine, does the integral converge? And sometimes you can just go ahead and integrate it. And if you're able to integrate it using those limits and it works out to be a number, yes, it converges and it converges to this value. Sometimes, though, we're looking at non-elementary functions that we just can't directly integrate. So what do we do in those cases? Well, there's a couple tests, and the first one is the direct comparison test. And the direct comparison test says, let's say that you have two functions, f and g, where on this interval, from a to infinity, both of them are positive, but f of x is going to always be less than or equal to g of x. Okay, from this point a forward, if you graph it, the graph of the f function is always going to be equal to or below the graph of g. Well, if g of x, the quote-unquote larger function, if that converges, then so will that smaller one. But then you can look at the flip. If that smaller one diverges, then so will the bigger one. And so we can use this as the direct comparison test. So looking at the integral here, does the integral from 1 to infinity of e to the negative x squared dx converge? We cannot directly integrate this. However, if you look at the picture that I have here, and I'll be honest, a lot of times when you're working these, if you've got that graphing calculator or a graphing tool, it can be helpful to graph these. But in this case, if you look in blue here, we have y equals e to the negative x squared. So that's in blue here. Well, starting at x equals 1 and going forward, it is going to be, that graph is going to be beneath the graph of y equals e to the negative x. Okay? So we could say that on the interval from 1 to infinity, okay, e to the negative x squared is less than or equal to e to the negative x. So this is my f, this is my g function, okay, going back to that direct comparison test. So that means that when I integrate, or when I look at the limit as I integrate from 1 to infinity, e to the negative x squared, it's going to be less than or equal to the limit for e to the negative x. So let me write that out. Sometimes it's easier to see it than to say it. Since this goes to infinity, I'm going to use a b. So we're looking at the limit as b approaches infinity of 1 to b, e to the negative x squared dx. Okay. Since this function is less than the function e to the negative x, this value here is going to be less than or equal to the limit as b approaches infinity, 1 to b e to the negative x dx. So I can't integrate the left side, but I can certainly take care of the right side. Remember, the left side is going to be less than or equal to whatever I get on the right. So working this out, I've got the limit as b approaches infinity. When we integrate e to the negative x, we get negative e to the negative x. And I'm going to evaluate that from 1 to b. So that's the limit as b approaches infinity. We get negative e to the negative b. So that's the same thing as 1 over e to the b. Minus a negative, so plus e to the negative 1, so that's 1 over e. Now, as b goes to infinity, e to the b is going to go to infinity as well. 1 over infinity goes to 0. So we have the limit of 0 plus 1 over e. Or sorry, the limit is 0 plus 1 over e, or just 1 over e. So that tells me that the limit as b approaches infinity of the integral from 1 to b of e to the negative x squared dx has to be less than or equal to 1 over e. Since it's less than or equal to this, that means it is going to converge to some point. So by the direct comparison test, this integral here will also converge. So yes, it converges. Now, there's a second comparison test, and I'm not going to do an example of this one just now, but I will come back later and do an example of this one. And that's the limit comparison test. And this one says if f and g are both positive functions that are continuous on the interval from a to infinity, if you take the limit as x approaches infinity of f of x over g of x, and you get a value L, okay? You get an actual number. It's going to be a positive number. Then the two functions are either going to both converge or both diverge. So when we use the limit comparison test, we'll be comparing a function where we're not sure if it converges or diverges, but we might have an idea one way or the other, and we'll compare it with a function that we definitely know it converges or diverges. And that very first example that I did, the 1 over x to the p, a lot of times those functions are used in the limit comparison test. And we'll actually do, I think, an example or two using those.